These are the common symbols that you see with reactions, so make sure you know those. Quiz on these on Friday. I'll give you a symbol or two, and you'll have to tell me what they mean. The first four right here, you've probably seen a couple of these already. These are your states of matter. All right. So when we start writing reactions like we're learning about this week, these are the states of matter. You start to see these. And when we get back from break and we start doing our unit on solutions in February, you will have to have states of matter with every single reaction, every single reactant and product that we write. Okay? A couple other forms. Arrows. If it's a down arrow, it's a solid precipitate. What's a precipitate? It means a solid forms. You're going to see this today in lab. Upward arrow means a gas. Just think about it, guys. Don't make it hard. Solids, what happens when you let go of a solid? It falls down to the ground. A gas, like a helium balloon, does what? Goes up. Gases generally will rise. Arrow, a single arrow, guys, just means produces or yields. Means a reaction has taken place. If you see a double arrow, it can go in the forward direction and the reverse direction. So it's a reversible reaction. You may see it like that right there. You may see it just like this, where it's just half arrows going both ways. It means the same thing. All right. When we get into equilibrium in the spring, this is how we will be writing a lot of those. Then you have specific settings or conditions that reactions may need as well, and that's what the rest of these arrows mean. If you see a triangle in the word heat, it means the reactants are heated. There needs to be something else used to get it going. All right. If you see something like kPa or a pressure unit, it means there has to be a specific pressure condition applied to your reaction to get the reaction to go. Likewise with a temperature. All right, it's still being heated or cooled. It's got to be at that specific temperature for it to happen. If you see an element, it could be palladium. That's a common example, but it could be any element, guys. It means a catalyst is needed. What does a catalyst do? It speeds up a reaction, okay? And we'll talk about why, when we do reaction mechanisms and things like that, why catalysts actually speed it up. But that'll come later on. And then if you see something like an E or an electricity or like the electron symbol, it just means electrolysis. There's electricity added to break it down. I think I have an electrolysis apparatus somewhere. If I can get it working, I will show you guys the electrolysis of water, but we'll see if that happens or not. All right, chemical equations and reactions. So you're going to be filling in the blank here as we go along. All right, so guys, what do chemical equations and reactions, what do they represent? Well, known facts. So all the reactants and products. Reactants are found where? First, second, last? Yeah, guys, reactants are the first ones that you see. They're on the left side of the reaction. Okay, left side, and then products are on the right side. Should be pretty basic, pretty simple. Reactants react together to produce products. That's the way that I think about it, and the way you should, because it's exactly what's happening. Reactants react together to produce products. So they're undergoing some type of change. You must make sure that you have correct formulas. Naming is crucial. That's why we've done naming already, and what's coming back to it. Like I've said all year long, if you can name compounds and do basic stoichiometry, you can do pretty much anything in this class. But you've got to be able to do those two essential techniques and skills to be successful in this class. So coefficients, we've seen those already a little bit with copper 2 sulfate pentahydrate, where it's got a coefficient out in front. They represent the number of moles. Okay, so the big numbers out in front tell you the number of moles. Subscripts are the number of elements in a formula. We've used those already as well, so it's nothing new. Notice what it says about subscripts. What do I have up there in big, bold, purple letters? They never change. Guys, star this, highlight it, circle it. They will never change. And what I mean by that is when we balance equations, which is what we're going to talk about today, which I think you may have done already in like middle school, they never change. Okay, only coefficients will change when we balance equations. The number of moles. If you change subscripts, what do you do to that substance? You change the substance. You change the properties. You change it to a completely different substance. Okay? The only time subscripts can change is when we're predicting products. Okay? Okay, they will have to change. Well, they don't have to. They may change or they may stay the same. Depends on what they're going to react with. All right, we'll get there later on this week. Okay, Wednesday, Thursday, and Friday is when we'll start talking about predicting products. But when we're balancing equations, they never change. All right, they never change. I'll add that in there. When balancing equations. You're going to see me abbreviate words a lot in this unit. Compounds, CPD or CPDS is how I abbreviate compounds. Equations, EQN or EQNS. All right. If I ever have an abbreviation up there that you don't know, just ask. Okay. Questions so far? All right, so when we balance equations, one thing you have to know are the diatomic molecules. Get your periodic tables out, your reference packets. This is something that people will struggle with throughout the year. I encourage you, it's one of those things. Master it now so you don't have to worry about it. You don't have to stress yourselves about it later on. Diatomic molecules, guys, they occur in pairs in their natural state, which means they are not alone. They're so reactive. Remember, it's all about getting to the lowest energy state possible. They will bond with themselves to be in a lower energy state because they're so reactive. But when they're together by themselves, all right, and when they're bonded with one another, they're stable. Okay? Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, hydrogen. Those are the 7 diatomics. There's many, many different ways that you can think about remembering them. Here's the way that I do. I don't use either of these sayings. If it works for you, that's great. To me, those are kind of more cumbersome. They're longer. This is how I remember it. Brinkelhoff. Brinkelhoff. Sounds like a Russian spy. Okay? Brinkelhoff. I always think that I'm going to actually, but I'm not artistic in any way. I'm going to draw a character to be Mr. Brinkelhoff. You know, he's a Russian spy, but I'm not good enough to do that. I can't. Mine would be like this. Oh, there he is. I don't even know how to do that. Oh, the hammer? The sickle and the hammer? Yeah, I have no way. I couldn't do it. I'm not an artist. That's why I went into the sciences. But Brinkelhoff, to this day, this is how I remember it, because I learned this from my chemistry teacher when I was in high school. This is how I still remember it, Brinkelhoff, right? Because now, when you write these, when they're by themselves in a formula, it's not bromine, they have a subscript of 2. So if you write it out by their symbols and put 2's down here, when you see them by themselves, it's a subscript of 2, the diatomics. These are naturally occurring in nature. Oxygen gas. Oxygen by itself is pretty volatile. Okay, but when you have it together, it's a stable molecule that we breathe in and we need to survive. Okay, nitrogen, same thing. Okay, so they're less reactive. Because they're so reactive when they're a single element by themselves, they want to bond with themselves to get to 8 so that they are more stable. Okay, so just remember Brinkelhoff. This is something we're going to see the rest of the school year. Okay, the rest of the year. So, when we're balancing equations, they must satisfy the law of conservation of matter. What does that mean? We've done it. It's review this year. Law of conservation of matter. It's like from Unit 1. Yeah, matter can't be created or destroyed. So that means that you're not going to have, say, on one side of a reaction, you have hydrogen plus oxygen. You're not going to have something like zinc as your product. Okay? You're going to have the same elements. Yeah, they may have different subscripts. They may have different amounts. That's okay, but you're not going to have some brand new substance that you didn't have before. Now, we're talking about ordinary chemical reactions. We're not talking about nuclear equations. We will talk about nuclear chemistry at the end of the school year, right before our Regents exam. That's when we'll do nuclear, where things kind of go out the window a little bit. Okay? But you must have the same type and number of atom on each side. So this is why we balance equations. That's what we're going to be talking about here today. How many of you balanced equations before? Maybe you have no idea what I'm talking about. We'll see. I'll come back and ask that question in a few minutes. All right. So when we balance equations, there's kind of a process that you want to go through here. So you want to start with the word equation. If they give it to you in words, you have to write the formulas, going from the names to the formulas of your compounds. Okay? if they don't give you the word equation, if I'm nice and I give you the equations already, you just got to start balancing. Super easy. So we're going to convert the two formula equations. Don't forget your diatomics. That's where if it says something like hydrogen plus chlorine reacts to form hydrochloric acid, and you have to write it out, you've got to remember that, hey, hydrogen's H2, chlorine is Cl2. All right, so then it affects it how you balance it. Balance with the coefficients, one element at a time. Polyatomics. This is why I've tried to encourage you guys, when we learned about our polyatomics back in Unit 5, to keep your parentheses around them. It's for this. All right, when I was talking before, it's looking into the future to say, hey, we're going to be balancing equations. Keep polyatomics together as a package deal if you can. Meaning, if you see the polyatomic ion on the left side and the right side of the equation, you're going to balance them together. You'll see what I mean as we go through and do some practice. Balance oxygen and hydrogen last. Check. Reduce coefficients down if possible. This is something people will forget, but you'll lose a point or two. Reduce them down just like we've done with subscripts with ionic compounds to get those into the smallest possible. And what's the thing we got to remember to never do? Never change your subscripts. Only when we predict products will, but we're only balancing right now. So, this is kind of my order to balance. This is what I have found to be kind of the fastest way to balance equations. I highly encourage you guys to jot this down in your notes. Doesn't mean you have to do it this way, but I've balanced thousands of reactions over the last 15 years. Okay? This is what I have found to be the fastest way to get to a balanced equation. Always start with your metals. Okay? They are typically the easiest ones to balance. And if you follow this, by the time you get to oxygen and hydrogen, a lot of times they're already balanced for you. Or they may make it easier to balance those ones. So metals first, polyatomics. If you see the polyatomic on the left and right side, if it's not on both sides, like if you don't see the same polyatomic on the reactant side and the product side of the reaction, you have to split it up into its individual elements. But if you see the same thing as a package deal on both sides, it's easier to just balance it as a whole. And you'll see what I mean. Then do the rest of your nonmetals that you haven't balanced already. Save oxygen and hydrogen to the end. And when you get to oxygen and hydrogen, one might be easier to balance than the other. Go with whatever one's easier first, and then hopefully it'll take care of the other ones. What tends to happen with oxygen and hydrogen, they're in a lot of compounds. Okay, they're two of the most common elements in the known universe. All right, so they are in most of the compounds that we're going to balance throughout the year. So we save those until the end, balance everything else first, and by the time you get to those, sometimes, a lot of times, they're already balanced. Or it's easier to balance them. But sometimes, because they're diatomics, you might have a half that you need to balance them. Do you think you can have a half of a mole? Like 0.5? When you're balancing? No, you can't, guys. Your coefficients are going to be whole numbers. So jot that down. Coefficients will be whole numbers. Okay, they're going to be whole numbers. And it's oxygen and hydrogen that sometimes you may need half of a mole, but we're going to double it. If you double that one, what else are you going to double? Everything. Just like we were doing it with empirical formulas in the last unit, okay? Multiply to a whole, don't round. All right, let's just jump in and start balancing some equations. Here's the first one. And the way that I do it, guys, I encourage you to as well. We're going to start by doing it like I'm going to show you, showing all the work. And that's what I want to see within this unit. Eventually, though, you want to be able to get so fast at this that you don't even have to write anything down. You can just do it by looking at it. That's by the end of the year, that's how you will balance equations. That's the goal. Okay? All right? So, right now, though, we're going to see some challenging ones. There's still reactions, guys. When I take a look at things, I have to write them down. Even though I've been doing it for 15 years or so, I still have to write them down at times. Some are easier than the others, and that's okay. So what I do is I'm going to write down all my elements on the left side. Remember, this is the reactant side, because they come first. And this is my product side of my reaction. Okay? Reactants and products. I should have the same elements on both sides of the reaction. So I've got phosphorus and phosphorus. I've got oxygen and I've got oxygen. How many phosphorus atoms do I have on the left side? 1. How many do I have on the right side? Okay. How many oxygens do I have on the left side? 2. How many do I have on the right side? 10, right? Subscripts tell you the number of atoms. Coefficients are how we're going to balance them. So I'm going to change up colors here. So now, what's the order that I was just kind of telling you that I have found to be the fastest? You don't have to do it that way, but it's the way that I found to be fastest. Metals. Do I have any metals? No. So go on to the next one. Then it would be, do I have any polyatomics? No, I don't. So now it's going on to my non-metals, but I'm saving what for last? Oxygen and hydrogen. So we have oxygen here. So do phosphorus first. All right. So I have 1 on the left and I have 4 on the right. 1 times what's going to get me to 4? Super easy. Now, where am I going to put that? Am I going to put 4 right here? Yeah, it's going to be a coefficient in my reaction, so it's going to go right out here. So now I have 4 on the left. Okay? So notice what I'm doing by bookkeeping here. When I've changed my coefficient, I'm going down here to change how many I have to show, oh, it's balanced. Okay? So, phosphorus is all balanced. Let's move on to oxygen. I've got 2 on the left. I've got 10 on the right. Does 2 go into 10 easily? Absolutely. How many? So if I put 5 up here, how many do I have on the left now? I'm balanced. So my coefficients would be 4, 5, 1. That's how I balance. That's an easy one. So I have 4 moles of phosphorus plus 5 moles of hydrogen, or excuse me, oxygen. That's going to yield 1 mole of tetraphosphorus decaoxide. Okay? That's what our reaction looks like. What's that? Decaoxide, yeah, same thing, yep. Easy? Yeah, that first one was. Let's move on and do some more. Here's another one. Write down, do your bookkeeping first. What elements do I have in my reactants? Sulfur and oxygen. Okay, and then on the right, I should have the same, which I do. What's going to be a little bit more challenging about this one, do you think? Nope, we don't have a polyatomic here. Why is this not a polyatomic?
There's no parentheses.
Nope, not that there's no parentheses. Is it an ion? No, it's not. So what is SO2? It's not sulfite. What is it?
Sulfur dioxide.
It's sulfur dioxide. There's no extra electrons given to it, so it's not a polyatomic. Remember, guys, polyatomic ions have a charge. Okay? So, how many sulfurs do I have on the left? 1. How many do I have on the right? Oh, those are balanced. I'm good there. How many oxygens total do I have on the left? 4. How many do I have on the right? Oh, that's a little bit more challenging. So what's going to be the most challenging part about this? On the left, how many different places do I have oxygen? It's in 2 different locations. So it's going to make it a little bit more challenging to figure this one out. It's like a puzzle. Okay, so you may have to change things around. This is why balancing equations, you should use a pencil, because you will probably be erasing a lot in this unit, and that's okay. All right, some of them are going to be a lot more challenging than others. Here's my little trick. On the left-hand side, I have an even number. On the right-hand side, I have an odd number. Okay? If I change on the left side, if I were to change a coefficient right here, what else will I change? Sulfur, okay? So do I really want to change my oxygen here? No, unless I have to. If I change it here, am I going to change my number of sulfurs? Absolutely, right? So when I see a problem like this, try to get your, if you have one that's an odd number and one that's an even number, try to get them to both be, both odds or both evens. It just makes it a little bit easier to balance. So 3, if I double it, if I start there and double it, what's that going to make now for the number of oxygens? Okay, so I got to put a 2 up here. What else did I just change? Okay, so sulfur now on the right-hand side is no longer 1. I'm going to have to change how many I have there. So I've got 2. Well, now I got to go back to the start. I've got 2 sulfurs on the right. I've got 1 on the left. What do I need to do to the left side?
2.
Yeah, I got to put a 2 right there. Well, what else did that just change by me changing that? Yeah, how many oxygens do I have on the left now? Oh, is that bad? No, it's actually good, right? So when you go back, excuse me, even if you had something balanced, we had sulfur balanced in the beginning, but as soon as we change something, we have to go back and reevaluate. That's why this bookkeeping method, guys, is so helpful, especially early on, and when we get into more challenging problems, which they're coming, all right? If you write them down, you kind of start to see one piece changing one element starts a chain reaction that does everything else that kind of will balance itself in the end. I want you guys to try example 3 on your own. So, what should we start with first, or what did I try to encourage you guys to start with? What's that? Metals. So I've got 1, I've got iron, so I'm going to change this to a 2. Super easy. Now, on the left-hand side, I have 3 oxygens. On the right-hand side, I have 1. How can I change that?
The 3 in front of each.
Yeah, put a 3 right here. So now I have 3 oxygens. Well, what else did that change by putting a 3 in front of the water? Yeah, now I have 6 hydrogens. So before I can move on, my ions are balanced, my oxygens are balanced, so the last thing is hydrogen. Well, let's take a look at the reaction. Is hydrogen by itself? Absolutely. It's super easy. Now it's much easier to balance hydrogen than it was maybe at first because it was by itself. Again, why we save oxygen and hydrogen until the end, guys? A lot of times they are either by themselves because they're diatomic, or what did we have right over here? Water. We had a water molecule. So a lot of times you're going to see water is a byproduct of a reaction or as a reactant. And that's why we save them until the end. So what do I need to do to balance this out? How many moles of hydrogen gas do I need? 3. That's going to give me 6. So my coefficients would be 1, 3, 2, 3. How'd we do? Good? All right. Number 4. Go ahead and try number 4. Yeah, now we have a polyatomic, guys. So when I start to go and balance this, now, you don't have to do it this way. It can be a little bit easier for you if you do. I'm going to start writing everything down. So I've got silver, I've got silver. I've got nitrate. Now notice, this one didn't have parentheses around it. Okay, we said if there's only 1 to balance it out, we don't need 1. So I'm going to add my parentheses whenever I see it. So I've got nitrate on both sides. If you see the polyatomic on both sides as a package deal, try to keep them together. It's going to be easier in the long run to balance them. Okay? You don't have to. You can break it up. That's your choice. But you're going to see, I think, how easy it can be. Then I've got calcium and I've got chlorine. All right. How many silvers on the left do I have? 1. How many on the right? How many nitrate ions on the left? 1, right? So I'm keeping it together. How many nitrates on the right? 2. How many calciums on the left? How many on the right? How many chlorines on the left? How many on the right? Okay. So now start going through. Do your metals first. How many metals do I have here? 2. Silver and calcium. Silver's balanced. Calcium is balanced. All right, I can move on to my next one. Now my polyatomics. How many polyatomics? How many nitrates do I have on the left? How many do I have on the right? So we need to get this to be 2. So what do I need to do then? Put a 2 up top as my coefficient. What else did that change by putting a 2 coefficient up there? Right, because notice, we haven't necessarily seen this, or I haven't, not that we haven't seen it, I haven't talked about it. Guys, when you have a coefficient, we talked about this back in Unit 5 a little bit, and in our last unit, Unit 6, with that copper 2-sulfate pentahydrate. Coefficients distribute out, and they change the number of everything in that compound. All right, so now we have 2 silvers, not just the 2 nitrates, so we've got to change that. So now go back to the beginning. Go back and do silver. Even though it was balanced, it's no longer balanced. So now, how many silvers do I need on the right? And I got to put a coefficient there. What else did I change? Oh, look. It just took care of itself. Right? So 2, 1, 1, 2 would be my coefficients here. Right? If you can keep the polyatomics together, I highly recommend doing that. It makes your life easier. All right, number 5. What's different about number 5? You have to write the formula down. This one's an easy one. What's our formula going to be for our equation? H2O. Now when it says breaks down, what does that mean? What does that mean for our equation? What are we going to use there to represent breaks down? What do you think? What do you think that term breaks down refers to happening in like lab?
It separates into H2.
Right, it separates into a hydrogen and oxygen. So what's occurring? A what? What's the name of our unit here?
Reaction.
Reaction, guys. That's kind of the terminology that says, hey, a reaction is taking place. So what symbol do we use to represent a reaction is taking place? An arrow. So those terms can change, but you've got to say, hey, anything that's talking about something's undergoing a reaction, that's when you have your arrow piece, saying, oh, it's yielding this. So water breaks down or yields hydrogen and oxygen. How do we write hydrogen and oxygen? Yeah. H2 plus O2. Why? Because they are diatomic. All right? So, we go ahead. Hydrogen, oxygen, oxygen. We've got 2 and 2, 1 and 2. Oxygen's the only thing we have to balance. How do we do that? That's going to make hydrogen to become 4, and then put a 2 right there. There we go. I want you guys to do the rest of the examples there on that page. When you have words going to formulas, guys, and you write your formulas out, if it's taking you more than like 3 or 4 minutes to balance an equation, go back and check to make sure you have gone from the name to the formula correctly. 9 times out of 10, if you can't balance an equation after like 2 or 3 minutes and it started as words, okay, you probably miswrote a formula. You probably need to go back and look at that. Oxygen gas, remember, is a diatomic, so it's O2. So CH4 plus O2 yields CO2 plus H2O. Now you can go ahead. We've got carbon, hydrogen, oxygen, 1 carbon. 4 hydrogens on the left, 2 on the right. We've got 2 oxygens on the left, and we have 3 oxygens on the right. Carbon is balanced. Go ahead and balance your hydrogens next. That's just the way I had them. It's easy to do. You need 4, so I'm going to put 2 here. That changes up my number of oxygens. So I now have a total of how many? 4. Okay. Carbon's balanced, hydrogen's balanced, oxygen needs to be balanced, so I need 4 here, which means I'm going to put a 2 up there. So 1, 2, 1, 2 is what you should have had for your coefficients. Questions on that one? Let me see thumbs up if we had it all right. Side if you were close, but all right. What are the next ones? I do not have those up there because I ran out of slides.
Calcium oxide.
Calcium oxide. Give me a second.